All right, hello, happy Friday. Today we are going to go through one new reaction. It'll be related to your bridge assignment, but we're not starting with the bridge assignment because that is kind of what we're going to get into at the end of the day. So you guys drew sugars. It was fine. They're a straight chain in a ring. I don't know about you, but when I was an undergrad, the idea that sugars could both be rings and straight chains at the same time didn't really make any sense to me, but I never asked anyone. It just seemed weird that in some books I would look at sugars and they would be given to me as a straight chain up and down, which I now know was a Fisher projection, but I didn't know that at the time. And then sometimes they would be shown as these little rings, but no one ever explained to me, and I never was willing to ask, why are they both at the same time? Well, they're not both at the same time, but they are in equilibria. And the reaction that changes them from a straight chain into a ring is the one that we're going to go through today. So today we're going to be looking at it mainly in terms of organic chemistry, but at the end of the day, we'll look at how it works in terms of biology as well. All right, so we are going to go through really only two reactions today. One of them is old, which is the formation of hydrates. So if you start off with a ketone, way back when we were naming ketones and aldehydes, I talked about how they could turn into hydrates, which look like this. All right, so Chloe, what is the difference between this ketone and this hydrate over here? What? Oh, do you want to be able to see things? Sure, I can turn this on. Wait on it. I can draw it on the board for you if you want to. Here, I'll draw it on the board. Everyone can see at the same time that that's forming up. All right, so this is a ketone, and this is a ketone hydrate. So what is the difference? Okay, so one has a double bonded O. What does the other one have atomically? So in terms of atoms. Okay, be more specific. It has more what? So one more oxygen and how many hydrogens? Two, right. So the difference here is one oxygen and two hydrogens. And what is one oxygen and two hydrogens? Yeah, which is water. So that's why we call it a ketone hydrate. There is not really water, so to speak, as part of this molecule, but the difference here is that this is a ketone. And just like when you're hydrated, you have extra water in your system or sufficient water in your system. We call this a hydrate because it has an extra O and two hydrogens. All right, so this reaction is adding in a water. Most of the reactions that we're gonna see today and for the rest of this outcome, which will be next on Monday as well, are going to be condensation reactions. So they go the other way. They actually kick water out. So if, much like when you have condensation form on the outside of a cold bottle or a cold glass or on your glasses or on your windshield or something like that, or your windows if it's cold inside, all of that water isn't really coming out of nowhere, it's coming out of the atmosphere. But condensation is the word that we use when water's seeming like it's coming out of nowhere. Right? It all comes from someone, but when it's being a product and you're finding water. And so this goes the other way around, we're adding water in. So when we spoke of this before, what we didn't do is go through the mechanism. So let's talk about how this actually happens. And it'll happen pretty easily in the presence of water and acid. And it's going to be reversible, but let's look at the possible reactions that can happen here. All right, Yesenia, you've got a ketone. What's the reactivity of a ketone? Right. It's an electrophile right at the carbonyl. But we know that it's not a super strong electrophile because what kind of nucleophiles react with ketones and aldehydes? Yeah, the fiercely strong ones. So this electrophile is fine, but it's not that strong in that you need a really, really strong nucleophile to attack it. Do we have a strong nucleophile in here? No, we don't. We got water, and how can water react? Yeah. Yeah, so it's got lone pairs, so it can be a nucleophile, it can be a base, but it's not a strong version of anything. It can also be an acid because it has a hydrogen to give away. But again, it's not a strong version of any of that stuff. So as it sits right now, your ketone and water don't really react together very readily. But by adding acid, I'm going to protonate something. So that's what acids always do, is they're going to put hydrogens on something. And looking at what we have in here, you can protonate one of two different places. You can either protonate the lone pairs on a water to make it H3O+, which is absolutely going to happen, but doesn't really get us anywhere. And you can protonate the oxygen on a ketone. And this is something we haven't seen before today. But this is what's going to happen that's going to get us toward our product. So let's compare and contrast the ketone versus our protonated ketone right here. So putting yourself in the shoes of a ketone, why is that carbon electrophilic? What do you think, Chloe? It wants more electrons. Why does it need more electrons? Who's pulling them away? Yeah. So the oxygen here in a normal ketone or aldehyde is pulling away on those electrons somewhat. But let's shift over to this protonated ketone. So now, thinking about the oxygen in a normal ketone, it's neutral, but it would like more electrons, so it pulls electrons away from carbon. What about over here? So now it's positive. How happy is oxygen with a positive charge? Not. It's really unstable. It has, not only would it like some more, but it is super grumpy. This is an angry oxygen that has not only less than it wants, but way less than it wants. So what it's going to do is take that out on its neighbors. And while a neutral oxygen will pull electrons away from carbon, a positively charged oxygen is going to be furiously pulling electrons away from carbon. So think about this carbon now. Normally, a carbon in a ketone is electrophilic. What about when it's attached to a double bond O+? More or less electrophilic? More. It's more electron deprived, so it's way more electrophilic. So in this case, we would have, this is a ridiculously strong electrophile. So now that you have a really, really, really fiercely strong electrophile, you don't need a strong nucleophile. Any nucleophile will do it. And so the only nucleophile that we have hanging around will be the water. So basically that carbon is so electron deprived, because the oxygen up here is so grumpy and fiercely pulling electrons, it's going to pull that water right on in there. And this is a mechanism we've seen before. Nucleophile attacks a carbonyl, kicks electrons up to the O. So after this step, I would have a carbon that's got an OH left over from the ketone. And now it's going to have an OH2+, which is just from that new water that just came in. All right, so the reactivity of O+, it's been a while, but O+ is a really good something. Leaving group, yes. So if this oxygen wants to leave, if it left, it would just pull these electrons down, so that carbon had 4 bonds, and it would just go backwards. So this whole thing is reversible. All of it can go towards product, and all of it can go backwards. This step can go backwards because you could just lose your OH+. This hydrogen could just be given away to water, which would just shift you back to a ketone. So this whole thing is reversible. So looking at this last step, how do you get from an O+ with 2 hydrogens to an OH neutral with only 1 hydrogen? What do we need to do? Yeah, just deprotonate. And deprotonating happens with any kind of base. It doesn't need to be strong. But in this case, to fit the bill, we just have water still hanging around. So this whole thing is just, I can just pull that hydrogen off and make that neutral. So what we see here is that it's really 3 steps. You've got acid base to protonate the oxygen, which makes it into a much stronger leaving group, which makes the carbon more electrophilic. And then we have nucleophile electrophile, where a water will attack your electrophile and ends up making another bond to an oxygen. And then you do acid base again, where you deprotonate and go back to being neutral. So it's just acid base, nucleophile electrophile, acid base. To look at this in reverse, in order to get from our hydrate back to this species, we would just have some acid protonate that OH, but all this whole thing is being done with acid and water. So while acid and water are not participating in every step, there's acid and water present in every step. And the whole thing just goes back and forth. And so this equilibria will favor different sides at different conditions, and it depends on which ketone or aldehyde you start with. But all ketones can turn into ketone hydrates in the presence of water, especially with acid. And so can all aldehydes. And I wanted to show you this mechanism, not because it's tremendously exciting or anything like that, but just to see how it works, because it's a really good model for the new reaction that we're going to do today, which we'll start on right now. So if we were to do this same type of reaction, but instead of adding acid and water, we were to add acid and alcohol, we will get a brand new functional group. We're going to add acid, and we could use any alcohol. So pick an alcohol. How many carbons do you want to add? 2. Great. So ethanol. Okay, perfect. All right, so ethanol is a lot like water in terms of reactivity. It's got an OH, so it's a weak acid. It's got an O with a lone pair, so it's a weak base, and a weak nucleophile. So by itself, it's not going to do very much. It's not a fiercely strong nucleophile, so it's not going to react with your ketone. But we've got this acid. So what happens in our first step here? It's going to look exactly like what we have above. Yep, we're going to protonate the oxygen. And this would give us that same situation where you have a ketone with an O plus at the top, which makes it significantly more reactive. Reactive in the same way, just much stronger. And once again, we could lose that hydrogen, so this reaction could go backwards, so this one is also completely reversible. All right. And now we have this carbon, and what's that carbon's reactivity? Yes, it's a strong electrophile. And now, what is the nucleophile that we have hanging around? You picked it, Chloe. So what's our nucleophile? Yeah. So the only thing that we have hanging around here that could be a nucleophile is the alcohol, because it's the only other thing that has a lone pair and can share electrons to make a new bond. So this should look very similar to the above reaction. Your nucleophile attacks that really strong electrophile, kicks electrons up to the O+, because that was a really good leaving group. The difference here is that instead of attaching a water, we're just attaching an alcohol. Because instead of attacking without water, we attacked with alcohol. And the reason why is because we didn't add water, we added alcohol. And whichever alcohol you add will react in the same way. So those of us in the classroom chose ethanol. So therefore we have O with 2 carbons. But if you had isopropanol, you would have an O with an isopropyl. You use methanol, it would be OCH3. If you had 7 carbons in a row in your alcohol, it would be whatever. So this doesn't really matter, it's just whatever was attached. All right, so what can we do now to make this thing neutral? Deprotonate it, perfect. And what do we have hanging around that's a weak base? Yep, once again, it's the alcohol. So remember that when we do a reaction, we don't just have one molecule. We have a bunch of things in our pot at the same time. So you got more alcohol. Some of your alcohol acts as nucleophiles, more molecules of it act like a base. And then we'll be at this new point at which we have this crazy functional group. So all of this is reversible. So hopefully this thing right here going from ketone to this new monstrosity looks very similar to going from a ketone to a hydrate. You have turned your oxygen of your carbonyl into an OH, and then you turned it from a double bond into a single bond. And so the pre-existing oxygen that was part of the ketone is now just an OH. And this chunk, this OCH2CH3, came from your alcohol, which you have now attached. This thing right here is called a hemiketal. But we started with a ketone. So that is a name of a functional group. It may come up It's not a very common functional group for us to name, but that is just what it's called. And this hemiketal, what does hemi mean? You have like hemisphere, half. So we are halfway to a ketal. So believe it or not, we're actually halfway through this reaction. The second half is going to follow the same steps though. Notice that it was acid-base to make your electrophile stronger, and then nucleophile attacks the electrophile, and then you deprotonate to make it neutral. The same thing happened here. Acid-base to make your electrophile a better electrophile, nucleophile attacks that electrophile, and then acid-base to make it neutral. So we're going to go through the same thing. So we still have acid. What can we protonate? There's two options. Yeah, so you could protonate this thing right here, and that would just send you backwards, right? And that's absolutely going to happen because this whole thing is reversible. You just go back in the other direction. Alternatively, you could protonate that OH right there. So let me pause for a second. A hemiketal is really a single carbon that's simultaneously both an alcohol and an ether. So it's kind of one of those combo functional groups, but not a very common one. But it's got an OH and an OR attached at the same time. This is what's going to relate to those sugars in a little while. All right, so at this point, we could protonate either of those oxygens. And if we protonate the one on the left, we don't get anywhere. But if we protonate the one on the right, we get to a new species that would look like this. All right, so this is just, we're still in the presence of our alcohol and our acid. And we're going to protonate that oxygen right there of the OH. And that would turn it into an OH2+. All right, so we answered this question already, but an O+ is a really good leaving group, which would make the carbon next door an electrophile, because leaving groups, when attached to carbons, make those carbons electrophiles. So you've got an electrophile. And what reacts with electrophiles? Nucleophiles. And still, the only nucleophile I have hanging around is still that little 2-carbon alcohol that we added in the first place. So I'm just going to write ethanol and acid on every step. You don't use the acid and the ethanol in every step, but you usually use one of them. But just so that we're keeping track of the fact that they're always there. Your alcohol is a nucleophile. It's not a very strong nucleophile, but this leaving group is a really good leaving group. So nucleophile attacks electrophile, kicks off the leaving group. And we would replace that O+ of this thing with an oxygen of an alcohol. So we still have this O ethyl group, but now what we'll have is another one that we just added in. It's got a plus charge on your oxygen. All right, and then how do we make that neutral? Deprotonated, perfect. And we can do that with any base, because an O+ is really strong acid. It's easy to pull the hydrogen off. And the only base we have hanging around is more of that alcohol, which will come on over here and grab that hydrogen. Same acid-base mechanism we've seen a whole bunch of times. We end up with a carbon that has 2 of these ethoxy groups attached. We got one of them there and one of them there. So notice we attached one to make a hemiketal. And now that we've attached 2, what do you think this is called? It's just the ketal. It's a full ketal. So it's all the way to a ketal. And that's what we call this guy. It's a ketal. So ketone is just a C double bond O. If you add another OH, then it turns into a ketone hydrate. But if you add an OR of like an ethoxy group, like an ether, it becomes a hemiketal. If you add 2 ORs, the second one will kick the OH off completely, and you end up with a ketal that has 2 ORs attached. So once again, we chose to use ethanol. So we had O ethyl groups. But if you chose to use isopropanol, you would have O isopropyls on both of those. And if you chose to use octanol, you would have an O with an 8-carbon chunk on both of those. So this is our one new reaction today. We're going to go through a lot of details about it, but that's it. It goes all the way from a ketone, which is double bond O, to a ketal, which is two ethers on the same carbon. What did we lose all along this way? There's something that we kicked out. It was in this step right here. What do we kick off as our leaving group? Yeah. So that chunk right there will just become water. So I'm going to shorthand this reaction up at the top here. We're getting rid of our hydrate. You don't need to do this entire mechanism. In fact, it's really repetitive. And what we see is that over and over again, it's the same three steps. Acid base, nucleophile, electrophile, acid base. Acid base, nucleophile, electrophile, acid base. So that's things we've seen a whole bunch of times. But overall, what happens is that a ketone and any alcohol in the presence of acid will turn into a ketal. It attaches an alcohol twice, making a carbon that's a diether, and you kick off water. And so this reaction is reversible, so the whole thing can go forward or backwards, but it turns out that we get to decide which way it goes, really based off of Le Chatelier's principle. So Le Chatelier's principle is something that I'm sure you heard about in Gen Chem. How well do you remember Le Chatelier's principle? No, totally fine. All right. So Le Chatelier's principle was tied into equilibria constants. And we a lot of times looked at those big Qs, but if you don't remember that, that's okay as well. The whole idea is for any equilibria that goes from product to reactant, we can steer which way it goes by adding or removing one of your molecules in the equilibrium. So if we add a whole bunch of alcohol, then we're increasing our concentration of starting materials, which will push our reaction towards product. If we add a whole bunch of a product molecule, like water in this case, then we're increasing the concentration of product, which would shift it back towards starting materials. Likewise, if we removed a bunch of alcohol, then we have a deficiency in reactants, so it would shift back towards reactants. If we remove a bunch of water, it would shift it towards products. So there's a lot of reactions that happen biologically in our bodies right now that are not energetically favorable, but they only go forward because if we use up all the products, even if it shifts forward like 1%, it'll keep moving as long as you keep removing your products. So the way that that matters for us right now is that if you added a whole bunch of alcohol, which way would you shift this equilibrium? To product, right. And if I've got this ketal and I want to undo it, I add a bunch of water, in which case it'll shift it back towards starting material. So really all you need to do to shift the ketone towards ketal is add alcohol and water. And all you need to do to shift it back is add, alcohol and acid, water and acid. So we always need acid, but if you add alcohol, you push it towards ketal. You add water, you push it back the other way. And so we get to determine which way it goes. Just for the sake of nomenclature, this was a ketone if it had R's on both sides, and we could turn it into or back to a ketal. If you start with an aldehyde instead, we don't call it a ketal anymore. We call it an acetal. So halfway would be a hemiacetal or a hemiketal. So it's no difference in terms of the reaction or the mechanism. The only difference here is a ketone would have carbons on both sides, an aldehyde would have a hydrogen on one side. So that's the only difference. So in terms of a ketone or an aldehyde, it doesn't really matter. It's just about a C double bond O turning into a diether at the same time. All right, any questions on that reaction? How are you feeling? Let's do an example. All right, if I were to start with benzaldehyde, which is this molecule right here, and I were to add a whole bunch of, let's go with isopropanol and acid, what would you get? What's that? So you need to add on the oxygen. So the O followed by that chunk. So this is an aldehyde, and we would be adding this chunk twice, this O isopropyl. You'd be kicking out water. The water would come from removing this oxygen right here. Put that really high at the top of the sheet. Hopefully you guys can see that, but it would just give you 2 O isopropyls there, one there and one there. And we would kick out water. Where'd the water come from? Yeah, exactly. It was that one original oxygen. If we go back a slide, you can kind of follow along that oxygen story. So it started off as an oxygen. It got turned into an OH plus, which got turned into an OH, which is still an OH. And then it got protonated and became an OH2 plus, and then it got kicked off as water. So it's that one original oxygen that becomes the water that you kick out. So this is a condensation reaction because we're kicking out water, we're producing water effectively. Going the backwards direction would be called hydrolysis. Lysis meaning water, or lysis meaning cutting, and hydro being water. So cutting with water is called hydrolysis and goes backwards the other way. But this would be an aldehyde goes into an acetal. All right, I'm going to give you another example, and this one's going to look weird, I'll warn you. All right, so instead of adding an alcohol, I'm going to add a diol. So I tell you what, instead of going all the way to the ketal, because this is a ketone, stop at the hemiketal. So just halfway through. You'll have an OH left over and you'll add this thing on. All right, it should look like this. We got one OH left over from my original oxygen in my carbonyl. And then I would have one of these guys attached. So it should look like that. Ready to go with that? All right, so here's how this guy is a little bit different. Normally what happens is we attach one alcohol, and then we have to have another alcohol come in and attack and be our nucleophile. But in this case, you don't need to wait for a different alcohol to attack because you have one that's already close by. And so this alcohol would be the second one that attacks. So it's kind of like if I ask you to hold up your right hand and grab a hand, what's the easiest way that your right hand can grab a hand? You're grabbing your other hand. You don't have to go look for someone else to just hold your own hands. And that's how we make rings. So this is going to make a ring, is that this alcohol becomes your second alcohol to come in there, and it's going to kick off the OH. And so the full-on ketal here would look like that. So notice that instead of two different OR groups, it's kind of like I have two different OR groups, but they're just attached to the same R group because you had two alcohols in your initial molecule. So it looks kind of silly, I bet, but this is a really practical application of this reaction. Basically, what we have done at this point is we have turned our ketone, which is an electrophile, into a ketal, which is not an electrophile anymore. And remember that this whole reaction is reversible just using acid and water. So it's not that big of a deal to turn it backwards. All right, so I want to talk to you a little bit about the idea of a protecting group. A protecting group is kind of like something that we do to a functional group to make it not reactive anymore. So it kind of removes its functionality. So as an example of this is also a cautionary tale. If you guys are doing retrosynthesis, which you should be working on sometime soon, if not already, if you ever have a molecule with multiple reactive sites, something's probably gonna go wrong. So usually we try to use molecules that only have one functional group at a time. But realistically, if we're building big drug molecules or something like that, they have a lot of functional groups and you can't only do one functional group at a time. So let's look at this molecule, for instance. It's got an aldehyde, which is an electrophile. And it also has an alkyl halide right here, which is an electrophile. If I add a nucleophile, you would have no good way of knowing which one it would attack. In fact, it would probably attack both, which creates problems if, let's say, I only wanted to attack the left part, I didn't want to attack the right part, I end up with issues. And so if I added, I don't even know, some strong, fiercely strong nucleophile, it might attack here, it might attack there, it might attack both, but you wouldn't get to choose. And if we're trying to come up with one specific reaction or to get to one specific target, we would want to make sure that only one of those is reactive. So what we can do is if we were to start with this molecule and add that ethylene glycol and acid, it would convert your aldehyde into this acetal, which is no longer reactive. So now you only have one reactive site, and now whatever reaction you do will only react here. But if we want to go ahead and undo this, we just add some acid and water and it just takes us back to where we were. So the idea here of a protecting group, and we have protecting groups for every functional group, but that's a little bit beyond the scope of this class. So we're not going to get into any of the rest of them. It's kind of like I put a little hat on your aldehyde, and so it's not reactive anymore. So by kind of putting a cap on it, it can't do anything. So you covered it up. And now you can react elsewhere. And then when you're done, you just take the cover back off and it's ready to go. Does that make sense? So it's practically a super great thing to be able to do. And we're not always or often looking to make acetals or ketals, but one of the really important applications of these is to have a protected ketone, which is also kind of what a ketal is. It's protected because it's not reactive anymore. And you can imagine any nucleophile you added now would only attack the one remaining electrophile, and so it wouldn't react with the right side. And we can do this selectively for aldehydes versus ketones as well, but it's one of the great applications of this type of reaction. So we're going to move into our biology stuff and our sugars in a second, but how do you feel about this reaction? You start with an aldehyde or a ketone, and you add alcohol. So you're just going to put two of those R groups on. You kick off water. So this is our first in the list of condensation reactions. We'll have more of them for Monday, but they're all going to kick this double bond O off completely and replace it with two bonds to something else. And you get water, which comes from that oxygen being kicked off. All right, I didn't grade any of your bridge assignments, but I assume that you could all look up and copy down the structure of glucose just fine. So a main reason for me to ask you to do that is so that you have glucose drawn in front of you. So if you guys have your bridge assignment, you can just pull it out. And that way you don't need to redraw glucose from scratch. So this is glucose. I'll draw it from scratch. It is 6 carbons in a row. And hopefully now you recognize this as a Fisher projection. It means that each of these internal carbons are all chiral. So this is D-glucose, and it has 4 chiral alcohols. So looking at the functional groups in this molecule, what do I have? What's this one? Aldehyde, and then just a whole bunch of alcohols. So going backwards to what we've been doing today, all of these reactions start with a ketone or aldehyde, and you add an alcohol. And so this cyclization of sugar is the ketone or aldehyde at the very top, plus one of the alcohols reacting together. But it kind of looks like we have a choice here. 1, 2, 3, 4, 5, 6. So your ketone your aldehyde right here is an electrophile, but we have a lot of different alcohols that could react with it. Make sense? And they could attack that thing and turn it into what would become a hemiacetal. All right, so let's imagine what would happen if that alcohol attacked. So what would I get if this oxygen made a new bond to that carbon? It'd be a little tiny one. See what would happen? Yeah, make a little tiny ring. How big would the ring be? Be carbon 1, carbon 2, and the oxygen. So it'd just be a 3-membered ring. All right, let's think back to last semester. A 3-membered ring basically looks like a triangle. Is that a stable ring? No, why not? Yeah, so the bond angles on sp3 carbons or oxygens are supposed to be 109.5, and these are 60. So the bond angles are way off. Furthermore, and it's been a long time since we did this, if you looked down those side bonds at the dihedral angle, you would see that everything is eclipsed, and that's really unstable. So basically, it's just bringing too many electrons together in too close of a space. And since this is happening on its own in solution, you guys, I mean, we're humans, right? So we're living things. So we're basically just a bunch of cells. And cells are kind of just like water balloons full of salt water, more or less, proteins and all of that, organelles. But this stuff is just sitting there in the interior solution, which is basically water of your cells. And they go back and forth doing this reaction on their own. But doing a reaction to make something unstable is just not going to happen on its own. So this reaction right here that I just drew is not going to work that way. The 3-membered ring is too unstable. So let's keep going down. If the alcohol from carbon number 3 attacks, I would once again be making a ring, but how big would this ring be? So 1, 2, 3, and then an oxygen. So a 4-membered ring. Have you even seen a 4-membered ring in this class before? No, why not? Why do you think? Same reason as the 3-membered ring. It's really unstable. So again, the bond angles would be 90 degrees, which is still not very close to 109.5. And the entire thing, all of those dihedral angles would be eclipsed. So that won't happen either. So now we're getting to the good and reasonable stuff. If the OH from carbon number 4 attached, now we'd have a 5-membered ring. So carbons 1, 2, 3, 4, and then an oxygen. So this would make a 5-membered ring. Our 5-membered ring is pretty stable. Yeah, they're okay. A cyclopentane is something that we've seen a lot, a cyclopentane ring. I mean, technically this wouldn't be cyclopentane because it's 4 carbons and an oxygen instead of 5 carbons, but it's still the same geometry. It would be okay. But what's our most stable ring, the one that we've seen the most? Yeah, 6. Those 6-membered rings are perfect. It's been a while since we went through the geometry, but you might remember that they make these chair structures where all of the internal angles are 109.5, which is just what they should be. And they can put those bonds axial or equatorial. The point is that they're always going to be perfectly staggered. So it ends up being, or very staggered. So the best ring to make, given the choice, and absolutely this molecule has a choice because it's got so many alcohols, bless you, is a 6-membered ring. So what we find is biologically, we end up with 2 sizes of rings in sugars that happen on their own all the time. One of them is a 6-membered ring and one of them is a 5-membered ring. The terms for those are furanoses and pyranoses. So you might hear about like fructopyranose and fructofuranose. And it's just that these sugars can make 6-membered rings and 5-membered rings all on their own. But the 6-membered ring is the most common, it's the most stable. So that's the one we'll look at right now. And so the OH of carbon number 5, once again, an alcohol is a nucleophile, can attack that carbonyl, which of this aldehyde is an electrophile, and it would make a new bond between the O here and that carbon. And so it would end up turning into a ring based on just that reaction alone. So let's look at what this ring would become. So we would have 5 carbons and an oxygen. So it's gonna look like, this is the way we usually draw it. But let's look at how our stereochemistry works out. So this is going to be our carbon number 1, 2, 3, 4, and 5. So imagine you take this thing and you tip it over. So basically what we're going to do is take this whole thing and imagine just tipping it down flat like that. So everything on the right would now be down. Everything on the left would now be up. Everybody got that? All right, so for carbon number 1, do you know where the OH is going to be? So the way that I've drawn it here, it would be up, but this carbon is not chiral, so it can spin around any way it wants to. So this carbon is actually flexible, and sometimes it'll be up and sometimes it'll be down. And so carbon number 1 is not defined because it wasn't chiral in the first place. 2, 3, 4, 5, well, 2 through 5 are chiral and they're stuck the way that they are. So these can only be one way. So if I take this carbon number 2 and basically push it down, the OH that's to the right would be where? Up or down? Taking this thing and pushing it right over. So everything that's sticking off to the right would then be pointing down. So on carbon number 2, you've got that OH, and when you tip it over, it would be sticking down. You guys see that? And then the H would be up. All right, what about for carbon number 3? When I tip that thing down, where's the OH, up or down? Up, yeah. H is down. All right, what about 4? Where's the OH? Down, yep. And so this should hopefully match what's in front of you already because you drew the ring structure. Number 5 gets a little bit more complicated because we don't have an OH and an H there anymore since we used the oxygen to make the ring. So stereochemically what happens is the H is going to be down and the rest of it, which is this chunk right here, the CH2OH, is not inside of the ring. Oops. So if it always looked weird to you when you saw these ring structures of sugars, they had one carbon that wasn't inside of the ring. Well, if we had all of those 6 carbons from your sugar in the ring and an oxygen, you would end up with a 7-membered ring, and 7-membered rings are nowhere near as stable as 6-membered rings. And so it makes this 6-membered ring, and then it's got kind of one carbon left out, and that's where that other carbon is. So with this carbon number 1, sometimes the OH is up and sometimes it's down, but the way that I've drawn it here with the OH up, that is called beta D-glucose. So this molecule is D-glucose. The beta and the alpha that you'll see in front of some of them sometimes, they tell you that it's in the ring form. And the beta means that that OH is up, and the alpha would mean that that OH is down, which isn't really a big structural difference when you look at it, but there's some really big stability implications. Again, we're gonna go back to last semester real quick. It's been a super long while since we did chairs, but if you have an OH on carbon number 1 that's up, and then for number 2, your OH is down, and for number 3, your OH is up, Number 4, your OH is down. And then for number 5, your big thing, which is a CH2OH, is up. Then for beta D glucose, you can have a chair structure where every single one of those, since they alternate up, down, up, down, up, down, up, down, are all equatorial at the same time, which is the best possible, in terms of stability, situation for any 6-membered ring, whether they're all 6 carbons or 5 carbons and an oxygen. So there's no great way for us to know why things in biology or in the world are exactly how they are, but it's pretty easy to speculate that beta D glucose, which is a sugar that is used in all living things, this is one of the currencies of life, right? Plants make glucose, we eat plants, maybe things eat us, but we're all passing sugar, and it's always in the form of glucose. We make other sugars, and some plants and living things make other sugars, but usually what happens is we turn them into glucose to feed them into glycolysis, and glycolysis is conserved across life. And so glucose, which, I mean, it might look random that this is the structure that we see for glucose, and why that sugar is more popular in life than the rest might not make sense. But when you turn it into a ring, you can see that it's the only one where every substituent is equatorial, meaning that it's the most stable possible sugar. And so what we have done here, bringing it back to our reaction for today, is that we took an alcohol, this alcohol right here, and we took an aldehyde, this aldehyde right here, and this carbon right here became what functional group? Notice this got an OH and an OR. Let's go backwards. So it started off as a carbonyl. A ketal or an acetal is when it's got 2 ethers on the same carbon, but that's not what we have. We have 1 ether and 1 alcohol. So we basically turned it into this thing, which in this case would be a hemiacetal. So the answer to this question that I brought up at the very beginning of class that I never understood or thought about as an undergrad was that sugars exist both as straight chains and rings because they go back and forth all by themselves in water all the time. And since you're made out of water, no offense, your sugars just go back and forth. I don't remember the ratio, it depends on temperature, but I think it's something like 70% of their time they spend as rings, like 30% of the time they spend as straight chains. But what we see is that these straight chains are what we break down for energy. So we have to kind of turn it into a straight chain to break it down through glycolysis. The ringed form is how we build it into bigger molecules like polysaccharides. And the reaction that happens in between that is formation of a hemiacetal, which is what this carbon is right here. So when I asked you guys to find the functional groups, I didn't expect anybody to come up with hemiacetal. But you can see that this right here, this carbon, has an alcohol and an ether. And that is the hallmark of a hemiacetal. Right, but hemiacetals are only halfway. So if I wanted to turn that carbon into an all the way acetal, what do I need to add? Another alcohol, right? So in our bodies, a lot of this happens in the presence of acid in an active site of an enzyme. A lot of this is enzyme regulated, but this reaction can go back and forth just in neutral pH as well. We try to force it in one way or the other using the acid, but it can happen pretty naturally on its own. But you do need the alcohol to make this happen. So this is gonna be, I'm gonna kind of shorthand these a little bit. Most of our multi-sugar linkages happen, at least for glucose, at carbons number 1 and 4. So in order to make it less confusing, I'm just going to draw it this way. Yes, there's more stuff here and here and here. All right, but this guy right here, this is your hemiacetal. And it's still electrophilic. It's the only one that's electrophilic. So it's the only one that can get attacked. And it would get attacked by another alcohol. But you can't make another ring out of the same sugar. So it needs to be the OH of another sugar. Oops. Doop. And so this OH right here of a carbon number 4 of another sugar is going to come in here and kick that OH off. Because remember, we kick off water to get towards our product. And that's what makes the linkage between one sugar and another sugar when we make polysaccharides. Is that Now we have a disaccharide where we attach 2 sugars together. And this disaccharide only has one hemiacetal, which is right there. And so you could join another sugar over here. Well, this is an alcohol, so it could attack the hemiacetal of another one. And you end up putting side to side a whole bunch of these sugars. And that's how we build glycogen, is we attach these things end to end over and over and over again. Starch is the same thing. Its glucose is attached 1 to 4 over and over and over again. Cellulose, which is what plants are mostly made out of, they're structural sugars, the difference is that they're in this beta position as opposed to the alpha position, but it's still just sugars attached like this, 1 to 4 over and over and over again. There's some cross linkages and other things, but that's the vast majority of it. And so at this point, looking at this carbon right here, I started off as an aldehyde. I turned it into a hemiacetal, which is what this thing is. But then once you've made that linkage with another sugar, now it's an OR on one side and an OR on the other. It's actually a full-on acetal. And once you get to the acetal, you can't attack it anymore. So now it's basically done. And we just attach these things end to end to end. And that is it. Any questions about this? You are doing this right now in your blood and in your cells. Congratulations, you are making hemiacetals and full acetals all day long and breaking them down again. If it's okay with you, you guys can have a free 7 minutes, and I will see you all in lab or class next week. Anybody on Zoom have any questions?
Sir.
Yes.
I said no, sir.
Oh, no, sir. Okay. Well, by all means, have a lovely weekend, and I'll see you all next week.
I do have one question, Dr. Ring.
Hit me.
For the previous stuff we were doing, where you had like an alcohol and it had the H plus on top of it. Where does that H plus come from? Is usually like on a reaction arrow.
Like this thing? It just means you add like some sulfuric acid to your reaction.
Oh, okay.
Usually when we say H plus, we don't care what acid it is. It's just a strong acid. And usually we just use a little bit of sulfuric acid. You might remember in lab a couple times, we put like some drops of sulfuric acid into a reaction. That's all we're doing here.
Okay.
Good question. All right, thanks everybody. Have a good weekend.